You plug a switch into the network, and within seconds, every port is flooded with broadcast traffic. The network grinds to a halt. This is a Layer 2 loop, and it kills networks in seconds. At Layer 3, routers have TTL to stop looping packets. Ethernet has no such field. A broadcast frame with no TTL loops forever, consuming bandwidth and CPU until the entire LAN goes down. Redundant connections cause these loops, and redundancy is essential. You need multiple paths, so one cable failure does not take down your network. But without a loop prevention mechanism, redundancy creates broadcast storms and MAC address flapping. Spanning tree protocol solves this problem. STP blocks redundant paths, leaving exactly one active route between any two switches. The blocked path stays physically connected and takes over instantly if an active link fails. STP works by running an algorithm with 3 steps. First, switches elect a root bridge. Every switch sends BPDUs declaring itself root. The switch with the lowest bridge ID wins. The BID is a 64-bit number made of a 16-bit priority and a 48-bit MAC address. Default priority is 32768. You can lower it to make a switch root, but only in increments of 4v96. Second, each non-root switch selects a root port, the port with the lowest path cost to the root bridge. If tied, the lowest neighbor bid breaks it. If still tied, the lowest neighbor port ID. Root cost values: 10 megabits equals 100. 100 megabits equals 19. 1 gigabits equals HUDL. 4,000, 1 gigabits equals 2. Third, each segment gets one designated port. The port on the switch with the lowest root cost becomes designated. If tied, the lowest BID wins. Non-designated ports go into blocking state, which is how STP breaks the loops. Now the ports transition through states. A newly enabled port starts in listening state for 15 seconds. It only processes and pointillegibly. Then it moves to learning state for another 15 seconds, where it builds the MAC address table. Finally, it enters forwarding state and carries traffic. If a port is non-designated, it goes straight to blocking and stays there. 3 timers control this. Hello timer is 2 seconds between BPDUs. Forward delay is 15 seconds per state. Max age is 20 seconds before a switch decides a BPDU path is dead. This means a topology change can take up to 50 seconds. 20 seconds waiting for max age, plus 15 for listening, plus 15 for learning. PortFast fixes the problem for end host ports. It skips listening and learning entirely, putting the port directly into forwarding. You enable it with the spanning tree PortFast command. Only use it on ports connected to end hosts, not other switches. BPDU Guard protects PortFast ports. If a PortFast port receives a BPDU, meaning someone plugged in a switch, BPDU Guard shuts the port down into error-disabled state. Enable it with spanning tree BPDU Guard enable. Best practice: enable PortFast and BPDU Guard together on all access ports. On the exam, expect questions on BID comparison, root port selection tiebreakers, port state transitions, timer calculations, and when to use PortFast versus BPDU Guard.